My name is Daud Ahmed, and this is the first lecture of the series on deep learning. Deep learning is all about neural networks, and the topic of this lecture is artificial neural networks. Artificial neural networks are computational models inspired by the human brain. An ANN or an artificial neural network consists of one or more layers. Each layer consists of one or more neurons. The neuron or the artificial neuron is the fundamental unit or the building block of the artificial neural network. This is the mathematical model of the neuron, or equivalently, the artificial neuron. It takes in k inputs. X1 is the first input, x2 is the second input, and xk is the kth input. For each input, the neuron associates a value or a weight. For x1, the associated weight is w1. For x2, the associated weight is w2. For xk, the associated weight is wk. What the neuron does is it multiplies each input by its corresponding weight. X1 is multiplied to w1 and then added to x2 multiplied by w2, which is added to x3 multiplied by w3 all up to k, where xk is multiplied with wk and the sum is taken and can be written as xiwi summation. After this, after calculating the summation, the neuron adds a bias value, and this is h, that is equal to this. Once the neuron calculates h, it passes h as an input to an activation function. The activation function can be a simple identity function that takes h as input, and this is the identity function, or it can be the sigmoid function, or it can be the ReLU function, the max of 0 or h. This is a sigmoid function, and it outputs a value between 0 and 1. This is the ReLU function or the rectified linear unit function, and what it does is if the input is below 0, it outputs a 0, and if the input is 0 or above, it outputs the input as it is. Now, what if we want to represent the inputs in the form of vectors and the weights as well in the form of vectors? X1, x2 up to xk can make up a vector. W1, W2 up to Wk can make up a vector. And if we look closely, this term is the dot product of the vector x and w. So what if we add the bias to the dot product? We get this. And then apply the activation function, which is f. So this is the mathematical equation of the artificial neuron that takes as input the x vector, the input vector, and has a vector of weights w for each of the input, and after calculation of the dot product adds the bias value, applies the activation function, and gives the O as the output. The artificial neural network is organized into layers. In an ANN, the data flows across layers. This is an example artificial neural network. The first layer is the input layer that takes in data from the real world and passes it on to the neural network. The final layer is the output layer, which produces the output of the network. Any layers in between the input layer and the output layer are called the hidden layers. In this scenario, we have two hidden layers, both having two neurons. The input to the first neuron in the hidden layer is all the outputs of the previous layer. That is, the input to this is k different values, x1, x2 to xk. Same for the second neuron, the input to this neuron is all the outputs of the previous layer. They are shown by lines 1, 2, 3. Same for this one 1, 2, 3. The inputs to the next hidden layer are all the outputs of the previous layer. So the input to this neuron in the second hidden layer is the output of this neuron and this neuron. This and this. Same for the second neuron in the hidden layer. The input is the output of each neuron in the previous layer. And same in the output layer, we have a single neuron, but the input to it is the output of each of the neurons of the previous layer. So its input is this and this. 1, 2, 3, 4, and 5. The ANN has 5 neurons in total. The data, it flows from input layer to output layer in the forward pass. And the data flows back from the output layer to the first hidden layer in the backward pass. The purpose of the hidden layer in the artificial neural network is to extract features from its inputs. The input to a hidden layer can be either directly from the input layer or it can be from a previous hidden layer. If there are k inputs to a hidden layer, then each neuron in that layer will have k weights, each weight corresponding to a neuron. This is an example hidden layer. There are 3 inputs to the hidden layer. So this neuron will have 3 weights, each corresponding to the 3 inputs. This neuron will also have 3 weights, each corresponding to these 3 inputs. If we want to find the vector, the dot product that we calculated earlier, if we want to find that for this neuron, we can simply do the following summation. x1 w11, x1 w11, x2 w12, x2 w12, x3 w13. This is a dot product. Essentially, this is the dot product between the input vector and the corresponding weight vector. This is the input vector x1, x2, x3, and this is the corresponding weight vector. X dot w1 is this dot product, and I have written this here. After that, we can add the bias value, and that is this expression. And finally, we apply an activation function, ReLU, softmax, or sigmoid, or some other choice. And then we get the output of this neuron. We follow the same process for this second neuron. And if we want the dot product, we can do x1 w21 plus x2 w22 plus x3 w23. And we get the dot product between the input vector and the weight vector of this neuron, w21, w21, w22, w22, w23, w23. And finally, after getting this term, I can add the bias vector to get this one and apply an activation. Apply an activation function and get O2. In deep learning, it is essential to work with matrices. What if we calculate the desired vector O, which has O1 and O2? That is O1 and O2. What we can do is write W1 and W2 together in a matrix like this: W11, W12, W13, W21, W22, W23 and multiply W with X. Add the biases and apply the activation function to all of this together. We will get O1 and O2. So matrix multiplication is the key here. It is calculating two dot products, the first and the second, and adding the corresponding biases. The output layer in the ANN produces the final result of the model. The number of neurons in this layer depends upon the task that we are performing with our ANN. If we are performing binary classification, that is predicting one of two outcomes, that is happy or sad, good or bad, yes or no, then we use exactly one neuron in the output layer along with the sigmoid activation function. Let h be the value that is calculated by the dot product and the bias addition. We apply the sigmoid activation function to h, and the output is if we are performing multiple classification, then we use multiple neurons. The number of neurons depends exactly upon the number of classes. If there are three classes, we can use three neurons. Let H1, H2, H3 be the outputs of each neuron before applying the activation function. Now we will apply softmax activation function. Softmax activation function transforms multiple values into probabilities. F of Hi will equal e power Hi by summation e power Hj. That means that we apply this function to each of these three. To apply it on H1, e power H1 divided by e power H1 plus e power H2 plus e power H3. To apply this to H2, we do the same thing and we follow a similar approach for H3. That is e power H3 divided by e power H1 plus e power H2 plus e power H3. When we sum up these three values, we get a 1. That is, the summed probability is 1. This is the probability of the first outcome, probability of the second outcome, and the probability of the third outcome. When we compare the three values, the maximum of these will return our desired class predicted by the neural network. In case of regression, the number of neurons can vary. It can be 1, 2 or anything, and no activation function is applied in case of regression model. No activation is also called identity activation.